Hi, and welcome to 4.4 Mass and Weight. Students will be able to describe the difference between and calculate mass and weight. So let's talk about how we can measure mass and weight. So for mass, we use something called a balance, which works by having a fulcrum in the middle, and you put the load on one side, and then you balance out by manipulating these three masses to balance out the load so that they're equal. And then you make sure that they're nice and balanced over here. Uh, and that'll tell you what the mass is. These numbers tell you the mass of the object that's placed on that side of the fulcrum. Again, it's all about balancing it out. You could also use an electronic balance if you are calibrated for Earth. And for weight, that's just straight up measuring how much force due to gravity is pulling on something. You don't need a whole fulcrum system or anything. You're just measuring the force exerted on the scale. Very similarly, you could have an electronic bathroom scale. This one looks like just an analog one. It's not electronic. But yeah, that's how you measure the force, the weight. So which one of these measurement tools would give you the same measurement on the Earth and the Moon? Pause the video and think about it. All right, so the one that would give you the same exact measurement regardless of the gravity is the triple beam balance. This is a true balance, okay, because the force might be less on either side when you go to the moon, but the change in the force is the same on both sides. So it ends up still balancing out and you would get the same numbers because those are reading out the actual mass of the object. Another critical thinking question, which one of these measurement tools is a fraud? Which one is not what it claims to be? So the electronic balance, you might have noticed, looks exactly the same as the bathroom scale, and it pretty much is. It's just reading out. You could manipulate this to read out a measurement in grams. So technically, it's giving you the mass. But if you take this to the moon or any other celestial body besides Earth, unless you calibrate it for the gravity that's at that position, it's going to give you the wrong mass. It's not measuring the mass, it's measuring the weight. And 99% of the time, if you're using this thing, you're using it on planet Earth, right? 100% of the time, let's be honest. So they could get away with saying, oh, it's a balance, it's an electronic balance. You might hear people say that, but really it's a scale. So these measure the weight, and this is the only one that really truly measures the mass. So mass versus weight, you might want to write this down in your notebook just so you have a good definition. Mass, and we use a lowercase m to denote the mass, is a measure of the amount of matter in an object. Mass is a fundamental property of matter. So how much matter does that object have? And we use units of kilograms. Weight, and you could either use a capital W, sometimes people use capital W. A lot of times I use F sub G because this is, in a nutshell, the definition of what weight is. It's the force due to gravity. The definition says the force with which an object is attracted to Earth or another celestial body. All right. The units for weight are newtons. But normally when we say, "Oh, how much do you weigh?" You could give a measurement in pounds, but you have to use newtons in all of our equations that we use. You'll never use pounds. You would always have to convert it into newtons in order to use our equations. So calculating weight. Weight is a force. We just said that. What formula do we use to find force? Well, we have a handy formula now. The first one we learned in the dynamics unit, F equals ma. But if an object is at rest, like you probably are right now, you might be sitting down, right? Do you have a weight still? Yes. But are you accelerating? Hmm. It doesn't, if you're just sitting still, you're not accelerating, right? You're an object at rest, staying at rest. There's no net force acting on you, no net force. So we want to try to find the weight but we're not accelerating. Can we really straight up use Newton's second law, or should we use kind of a version of it? It says, does that mean we have no weight when we sit down? So there's kind of a backstory to little g. Like it's not, we didn't give you the full picture in unit 3 when we talked about acceleration due to gravity. So the units for that was meters per second squared. It's a measure of the rate at which an object falls because of gravity's pull. And on Earth, we said it was negative 9.8 meters per second squared. Okay. So that is how fast you would accelerate. That is your rate of change of velocity on Earth, negative 9.8 meters per second every second. But there's a different way to define little g. All right. So instead of the acceleration due to gravity, we can say, ooh, that is the gravitational field strength, the strength of the gravitational field around Earth. And the units for that version of little g is newtons per kilogram. Newtons per kilogram for gravitational field strength. So basically, if you have an object, okay, then you have the force due to gravity acting on that object. Well, you're in Earth's gravitational field. Here's Earth. It's orange for some reason. Maybe it's Mars. Okay. There is a field, a gravitational field around that object. Okay. Pulling you towards the center. And the strength of that field gets stronger as you get closer to the surface and further away. So the gravitational field strength says, how many newtons do you feel? How much force? How many newtons do you feel per kilogram that's at this position? So if you had 1 kilogram, you would feel how many newtons? On Earth, it's 9.81 newtons for every kilogram of mass that you have near Earth's surface. So if you have 1 kilogram, you would feel 9.8 newtons of force. That's how strong the field is. So that explanation kind of boils down to this. It's a measure of how strong the gravitational field is around a celestial object. Now, can you prove, we're saying that it's the same thing. Little g, you could say 9.8 meters per second squared, or you could say 9.8 newtons per kilogram. Those two units look very different. Can you prove that a newton per kilogram is equivalent to a meters per second squared, and how would you do so? We're going to answer that question a little bit later in this presentation. So back to Newton's second law, if F equals ma, and we know that we're talking about the acceleration due to gravity, which is equivalent to the gravitational field strength, we're going to use W equals mg. The weight is equal to the mass times your acceleration due to gravity. And like I said before, I like to use Fg equals mg because this is, again, the definition of the weight. It is the force due to gravity. This is a subscript, so I'm going to be saying Fg equals mg a lot. I'm not saying that F times g is equal to m times g, because then the force would be equal to the mass. The weight would be equal to the mass, and that's not what we're saying. The whole point of this is that it's different. So it's Fg, F sub g is equal to m times g, the acceleration due to gravity, or we just learned the gravitational field strength. So before we were kind of like, well, if I'm sitting down, I'm not accelerating. True, but you're still in a gravitational field, and that field has a certain strength. So all you have to do is take your mass and multiply it by that physical property, gravitational field strength. And the more mass you have, the more weight you'll have. And the stronger the gravitational field strength, the more weight you will feel. So that is how Newton's second law turns into our weight equation. Fg is equal to mg. So where is the equation for gravitational field strength? Ooh. On the back page in the mechanics section, So this was Newton's second law. So we're kind of skipping a little. Next unit, we're going to deal with friction. In unit 6, this is Newton's law of universal gravitation. And then here it is. Little g is equal to Fg over m, which is kind of like the same form as how they had Newton's second law. So you could see the similarity there. They replaced the A with the G and replaced the net force with the weight. If you want, you could write next to it F sub G is equal to mg. Same as if you didn't do this already, you could also put that form in your reference table if you want. So back to that question. Can you prove that a Newton per kilogram is equivalent to a meters per second squared? Well, using that equation that we just found, we could say that G is equal to Fg over m. So the units for the gravitational field strength is equal to Fg is measured in newtons, mass is measured in kilograms. Okay. We could go a little bit further and we could say, well, Newton's second law says A is equal to the net force divided by the mass, and a meter per second squared, that's the acceleration, is equal to the net force is newtons over kilogram. So that's all you really need. But remember, if we wanted to even take it further, the net F equals ma. So we could say, okay, a newton is equal to a kilogram times a meter per second squared. So we can plug in this over here, and we could say meters per second squared is equal to kilogram meters per second squared over kilogram. So I just plugged this in over here. And now cancel, cancel, and you could see that this is simply saying a meter per second squared is equal to a meter per second squared. So it all evens out, no matter how you look at it. And then G, we said, okay, the units for G in unit 3 is a meter per second squared. It's the acceleration due to gravity, which is equivalent to the gravitational field strength. So G equals G. G is G. Okay, the gravitational field strength is the acceleration due to gravity. You're just changing the units and how you're thinking about what's happening here. So let's do an example. It says the average astronaut has a mass of 80 kilograms. The spacesuit has a mass of 140 kilograms. What is the total mass of the astronaut and the suit? What is the weight of the astronaut and suit on Earth? And what is their weight in pounds? And oh, look at that conversion factor. 1 Newton is equal to 0.225 pounds. So I made this slide a while ago. Does anybody recognize what this background is? That used to be, I think it was like Windows XP, that background. I don't know if you'll even recognize that anymore. Okay, so let's do the problem. The total mass is just the mass of the person plus the spacesuit. So what is their weight on Earth? Like how heavy is that spacesuit and them together? Let's do the formula. So we know that the mass is equal to 220 kilograms, the total mass. And we know that G is equal to negative 9.8. I think I just said 9.8 before. I was talking about the magnitude. That's okay when you're talking about the magnitude. But now we're doing an equation. Gravity's pointing downward. And it's up to you. You could say meters per second squared still, or if you want to try out the newtons per, let's be fancy. 9.8 newtons per kilogram. We just learned some new stuff. All right, and then the weight is the force due to gravity. All right, so Fg is equal to mg. F sub g is equal to the mass times the gravitational field strength. So Fg is equal to 220 kilograms times negative 9.8 newtons per kilogram. And we could already see that if we do some unit analysis, the kilograms are going to cancel out, leaving just newtons, which is the unit for the force due to gravity. So when you do that multiplication, you get a force due to gravity, or a weight of 2,156 newtons downward. You get a negative number, and that's what the weight is telling you. The force is pulling you downward. Your weight is pulling you downward. Okay, 2,000 newtons. how heavy is that really? Let's convert it into pounds so we get a better idea of what that weight is equal to. So you write the number down with its units, please. And then you multiply by some parentheses. Put a line in the middle. Don't make it a distraction because we're going to make a really cool fraction. Write the units that you just wrote on the opposite side so that they cancel out, leaving you with pride. Write the units that you want in the only blank space. Now you're ready for some numbers to take their place. How many of one thing equals the other? That's the question we've been asking for a really long time. So 1 Newton is equal to 0.225 pounds. Multiply the numerator, then the denominator. Simplifying units makes me feel phenomenator. So that is a whopping 485.1 pounds. That's heavy. How does this person walk around carrying almost 500 pounds? Could you walk around with all that? Well, that's really the mass of them and their spacesuit together. But still, like the spacesuit weighs more than they do. It has more mass than the astronaut does. I hope they go somewhere different where their weight is less. Maybe our astronaut is going to go to the moon. So the gravitational field strength on the moon is about 1/6 of Earth's. What is the total mass of the astronaut and suit? What is the gravitational field strength on the moon? And what is their weight on the moon? So these questions are a little bit different. First of all, this one's always like a trick that they'll throw at you, okay? The mass stays the same. Remember the definition of mass? It's the amount of matter that comprises an object. Well, the person didn't lose any of their matter. They didn't like cut off a limb or go on a crazy diet or anything. They didn't lose mass, and the spacesuit is still made of the same amount of matter, so they didn't lose any mass. So no work necessary for that first part. What color should I use here? Maybe red. So the mass is still, what did we say it was? 220 kilograms. The mass doesn't change if your gravitational field strength changes. Okay, the mass stays the same unless they say you lost mass. Okay, but just because the gravity is different doesn't mean you changed your mass. So the mass stayed the same, but the gravitational field strength is now 1/6 of that on Earth. So we can write it like this: the gravitational field strength sub the moon, the gravitational field strength on the moon is 1/6 that on Earth. And we know the gravitational field strength on the Earth, so we can plug in 1/6 times negative 9.8 meters per second squared, but they're saying the gravitational field strength, so let's give units for gravitational field strength since they're asking about that. And we can say that the gravitational field strength on the moon is about 1.6 newtons per kilogram downward. Okay. Then it says, what is their weight on the moon? So look at that. Now we have enough information to use our equation. So Fg is equal to mg. The weight on the moon is equal to, the mass stays the same, but there's a weaker gravitational field now, 1.6 newtons per kilogram. So your new weight decreased to about 359 newtons downward, which is much less in, I forget what the newtons was before, but when you multiply by that conversion factor, that turns into about 80.8 pounds. For you, the astronaut, and the spacesuit together are only 80.8 pounds. You are effectively 1/6 as heavy. So that's pretty crazy. It's like there's you, and then picture 6 smaller yous that add up to your total weight. I don't know if that's a weird analogy to make, but yeah, there's much less gravity on the moon, but there still is gravity on the moon. I hear it all the time. Students say, "Oh, there's no gravity on the moon." There is gravity on the moon, everybody. Okay, it's just weaker. Okay, don't count it out just because it's weaker. Even the weak shall inherit the earth. No, I don't know. But the moon, okay, has gravity. Don't tell me the moon doesn't have gravity. You know what the moon doesn't have? An atmosphere. Okay? Though you could say the moon doesn't have an atmosphere, but if you come up to me and say the moon doesn't have gravity, we're gonna have problems. All right? It's 1/6 as great as Earth's because the moon is less massive than the Earth is. All right, it's 20 minutes in. We do have this other example here. It says the astronaut travels to planet X, where the combined weight of them and their suit is now 3,366 newtons. What is the gravitational field strength on planet X? What is the acceleration due to gravity on planet X? So we don't know how strong the field is. We have to calculate it based on this new weight. Maybe they brought one of those scales with them and they could read the force. They know how much force they're being pulled down with, but they don't know what the field strength is. But they do know one thing. Their mass is still the same. So the mass is equal to 220 kilograms still. They know their weight is equal to 3,366 newtons. And remember, the big capital N stands for the force. So if you're ever confused on what is given, just know that that's the force. So they're asking for the gravitational field strength. So you use this version, plug in your numbers, and you get a gravitational field strength of 15.3. And then what are our units? Remember, newtons per kilogram. That is for gravitational field strength. And they're saying, what is the acceleration due to gravity? It's the same magnitude. It's not even a different direction. Oh, and by the way, this should technically be negative if we're talking about direction. You choose to make it going downward because you know that the weight is pointing downward. And so, yeah, the only difference is not the direction, but the units when you're talking about the difference between acceleration due to gravity, meters per second squared, and the gravitational field strength. Really cool stuff. So there are these two videos that I normally show when I do the lecture in class. I think they're really great. I'm going to put them in the extension folder for this unit. Chris Hadfield is an astronaut who was on the International Space Station. He was a commander of, I think, more than one mission, I think. But I'd like to show this video here because it shows, you know, we live and die in a gravitational field. Most people do. So we take it for granted. We're not just in a gravitational field, but Earth's gravitational field. So we all have this shared experience that we can never escape unless we go somewhere where you appear to be weightless. So Chris Hadfield's in the International Space Station here, and I just want to show you this so you kind of like break the um, perception that their Earth's gravitational field is like that everywhere in the universe. So this is kind of showing that it can change. And Chris Hadfield on Earth, this is kind of a funny video to show after. So check that out. Oh man, so it says, what is the ball's acceleration? So in that video, he throws a ball upward. And I just wanted to point out that, and we kind of talked about this in the last unit. What is the ball's acceleration? It's negative 9.8 meters per second squared the entire time. Even at this position, it's still accelerating downward meters per second squared. Because did the gravitational field strength change just because the ball is moving now and it's at the apex of its flight where the velocity is zero? No, the gravitational field is still the same. He didn't throw that ball into orbit or anything like that. So yeah, even in orbit, the gravitational field is pretty much the same strength. So yeah, think about that. If the gravitational field is pretty much the same strength, even on the ISS, then why are they weightless? What? The ball's mass is 0.5 kilograms. With what force is the Earth pulling on the ball? Pause the video and think about it. Do a calculation. And what is the net force acting on the ball? Pause the video and think about it. So here's the calculation for the weight. It's negative 4.9 newtons. And if we make a free body diagram for the ball, what are some forces that are acting on this ball right now? You might say the weight. Are there any other forces if you neglect air resistance? No, there aren't. So actually, the net force in this situation, not always, but in this particular situation right now, there's no other forces on it acting on it besides gravity. So the net force is also 4.9 newtons. Now, obviously, the whole point of a free body diagram is some situations might be different. If you have an applied force or anything else like that, you'd have to analyze it differently. But that's how you analyze that particular situation. And that's about it. Thanks for watching and have a great day.